So, students, today we'll discuss some basic things about spherical mirrors. Now, the first question is, what are spherical mirrors and what is the difference between spherical mirror and plane mirror? Well, the mirror in our houses in which we see ourselves daily is a plane mirror. So, this is a mirror. If you are here, your image will be here. It's a plane mirror. We need spherical mirrors when we want to cover more areas or other applications. Spherical mirrors, as the name suggests, they are they can be considered to be part of a sphere. So they are mirrors like this. Either in the center they are bulging out, means bulging out perpendicular to the plane of the paper. So from the side they look like this. This portion of the spherical mirror, if it is polished, I mean once we polish the surface, once we clean the surface, once we rub the surface with proper things, once we polish it, it becomes a reflecting surface. You must have seen, students, in case you have a plain mirror in front of you which is full of dust, you won't be able to properly see your image on the other side of the mirror. So that's the reason we polish the mirror to make it reflecting surface. Now the other side, let's say these lines, they show that the mirror is shaded. If it's this side is shaded and this side which is bulging outside is a polished surface, this mirror is known as convex mirror. This is first type of spherical mirror. Now, students, the same spherical mirror, if you make this side what? Shaded area, and the inside side, you see from the center, if this was a plane mirror, from the center it's going inside. It's going inside, it's not bulging outside. The reflecting surface, is going inside. So this is a good example of concave mirror. Now, both convex mirror and concave mirror are used for different applications. You must have seen convex mirror, convex spherical mirrors, attached to the rooftops to cover a very large area. This couldn't have been done by a plane mirror here. Now let's discuss some basic things about mirrors. And now guys, let's say this is our concave mirror. Now, obviously, this is the shaded area, the bulging side is the shaded area, and inside this is a reflecting surface. This is concave in shape. This is reflecting surface. Now guys, the center of the mirror which we can see, which we can touch, is known as pole. the center of the mirror. It's like if this is a spoon, right? Let's say this is a spoon. Now we put the food inside. We put the food inside. So let's say if this outer bulging area is shaded and inside is polished, this is a good example of a concave mirror. Now the center of this whole inside surface, the center of this somewhere here would be the pole, right? And when you see this from this side, from the side, the spoon, this portion will look like this. So this is the pole. Now this line is the principal axis. It's on the principal axis, the pole lies. Now guys, you must have done some fun maybe at lower classes. You see, you must have remembered having a convex lens with you. Now guys, see, it's a new concept, lens. A mirror has one reflecting surface, whether inside one or the outside one. But a lens has two reflecting surfaces, both this side as well as this side. Now you see that guys, when the rays come from sun, rays coming from a very distant object are parallel. When these rays come, you must have seen that on these rays, well, it also has the principal axis. It's the principal axis of this convex lens. Why convex? Because it is bulging outside. You know, now from the center it's bulging outside. Now, if you place a paper, let's say here, maybe nothing happens. If you place a paper, maybe nothing happens. If you place a paper, maybe nothing happens. Now, once you keep shifting different position of paper, you will see at one position, especially you will find a hole. You will kind of hole here, a point here, getting blackened, and immediately, in case it is full sun, it catches fire. This point is the point why it caught fire, because these rays coming from sun, they also carry heat energy with them. Now, every ray is associated with some heat energy, and a lot of rays, millions of rays coming in, all getting refracted at one point, getting focused at one point, getting concentrated at one point, possibly compel the opticians or scientists to name this point on the principal axis as focus. So focus is the point where when the rays are supposedly coming from a very distant object, let's say sun, which is at infinity, these rays will always get focused on a point, and a lot of heat energy concentrated at one point, so it results in burning of the paper. Sometimes the children, they focus the lens without the other person knowing it on the shirt, on the back or something. So and there's a hole in the shirt, it starts burning. So this is a concept I'm telling you, that in case of our concave mirror, now we expect when the rays are coming from infinity, they'll come like this, all the rays would be parallel, and students, these rays are the incident rays in black color. Even on the principal axis also there's a ray in black color, and guys, in the red color I will draw the reflected ray. Now this ray will get reflected, so this is the point. This ray will get reflected, so all the rays are getting reflected. Interestingly, all the rays getting reflected, they will pass through one common point which is known as F. And since this is lying on principal axis, we call it principal focus. This is my principal axis and this is principal focus. All right. So you can also say on the principal axis, focus is there, and the distance, let's say the pole is represented by, let's say it is represented by P. So FP distance, that is distance between the principal focus and the pole, students, is known as focal length of the mirror. It's the same case in the lens also. This is the focal length of the lens. We'll discuss lens in detail. The only difference in case of lens, the center point is, we cannot touch the center point. It's inside the lens. It's known as optical center. Optical center. And in case of a mirror, it's known as a pole. Now guys, you see that, see guys, we have this concave mirror. Let's say the concave mirror is this. Now if we complete the circle of the concave mirror, students, there will be a center of this circle, right, in 2D. Actually, concave mirror is a 3D thing. So obviously, if you extend it in all the directions, this mirror, you know, if you extend it in all the directions, it will result in a sphere. Hope you can understand. Now, the center of that sphere is known as center of curvature. Center of curvature. So I hope the concept is clear. Whatever spherical lens, whether you have a concave lens or a convex lens, let's say you extend all the sides, you know, in an imaginary way, you extend all the side, it will result in a sphere. It will result in a sphere. The center of that sphere is known as center of curvature, and that also lies on principal axis. So I'm getting back. Center of, again, now let's say, students, if you extend this sphere like this, so here somewhere will be center of curvature, and this is represented by C. So I'll write here center of curvature. I'm representing it by C. Now guys, this length CP, that is between the center of curvature and pole, is known as radius of curvature. So students, what is radius of curvature? It is the distance between center of curvature on the principal axis and pole of the mirror, CP. Guys, now comes the third thing, aperture. Aperture. You see, it's the diameter of the reflecting surface of the mirror, whether it is concave or convex. I'll tell you. See guys, if you draw, let's say this is your maybe concave mirror or convex mirror. So this is the center, guys, and you see this diameter of the reflecting surface. This whole surface is reflecting, right? This diameter is known as aperture. Now guys, you see, for small, very important thing, only in case of spherical mirrors with small apertures. Small apertures mean small surface area, you know, and the diameter of that surface area is the aperture. For small apertures, spherical mirrors, whether they are concave mirrors or whether they are convex mirrors. This is the case of a convex mirror where the reflecting surface is bulging outside from the center. Remember guys, the focal length Fp is represented by letter F, is half of radius of curvature, and radius of curvature is Cp. Or in other words, you can say Cp, the radius of curvature for spherical mirrors of small apertures is always double the focal length. You could use this formula to solve so many numericals. All right, students.